And Jack, I've started the recording, so you can start when you're ready.
Thank you, Jeff. Good morning, everyone, or evening, depending on where you are in the world. Thank you for joining. My name is Jack Castro. I've been with MSC since 1987, and I've been working in the technical side of MSC for all these years. The last 18 or so years I've been working in Seattle, Washington, closely with the Boeing company on everything from stress through loads and many other things over the years. I'm going to talk to you today about MSC Flightloads as a tool for doublet lattice aeroelastic analysis. I only have 45 minutes, and so I'm just going to really scratch the surface, but I'm going to show some of the features and capabilities in MSC Flightloads that are of most interest to the customers that I work with. And as I teach this class, we have a 3 to 5 day Nastran aeroelasticity and Flightloads class. And so the features that I'll be covering today are some of the highlights that are covered in that class in much more depth. This is also not comprehensive. There's a lot of other capability. I'm not going to be talking anything about Nastran integration with CFD or anything like that. There's a few hooks in place for some of that, but that's a whole nother, probably worthy of a whole nother presentation. So we're just going to focus just purely on doublet lattice and a little bit on the basics of Nastran aeroelasticity and the interface of the MSC Flightloads product. So I'll start out today with just a very brief overview about what is aeroelasticity, just a couple of slides there. I'll summarize sort of the 3 pillars of aeroelastic analysis available in Nastran out of the box. And then I'm going to talk a little bit what is the MSC Flightloads product. And we're going to go and show you some basic feature demonstrations, showing you how you can import and visualize your doublet lattice meshes, how you can create the aerostructure coupling using splines, and how you can validate them. I'll talk a little bit about creation and display of the monitor points. Monitor points are just load integration tools, arbitrary about any location in space on any collection of nodes in your model for either internal or external loads. And then I'll show a little bit on the pulse processing side. We'll look at a 1G level flight Flightloads display on the airframe and on the aero mesh. And I'll finish off with just showing a little bit about the flutter mode animation capabilities. And then we've got the question and answer. Okay, so what is aeroelasticity? Aeroelasticity is essentially the analysis that takes into account the exchange of energy between the elastic forces of the structure, the inertial forces due to structural accelerations and structural motion, and then the aerodynamic forces. And depending on which 2 or 3 of these physics are interplaying at any given time, you get various sorts of solution effects. So all the aeroelastic solutions are typically interplay of these three physics. Now in Nastran, there's really 3 primary aeroelastic solutions or capabilities. The first is static aeroelasticity with trim that happens to be hosted in something we call solution 144. And this is kind of one form of the equation of motion, but basically what you can see in this equation of motion is you've got mass times acceleration, you've got stiffness times displacement. Now you've got also the forces here due to the motion of the structure. So as the structure deforms, UF is the displacement, so as the structure deforms, you get another aeroelastic effect or aerodynamic effect causing force. On the right-hand side, you have whatever applied loads the user happens to have, such as fuselage pressures and things like that. But you also get additional aerodynamic loads due to the deflection of controllers. And controllers, I say generically, this could be things like angle of attack, elevator deflections, things like that. So this is the equation of motion that's solved. And we solve it at a steady state, so it's a static solution. And the outputs are the trim parameters, loads on the structure and on the aerodynamics, as well as stability, control derivatives, and there's an option to also compute the divergence speed. The other second solution sequence in Nastran that people frequently use with doublet lattice is our flutter solution. It's hosted in solution 145. And this is basically a complex eigenvalue equation where you've got, I'm showing it in generalized coordinates here, you've got generalized mass, generalized damping, generalized stiffness, and a generalized aerodynamic matrix that's a function of Mach number and reduced frequency. And this equation takes many different forms depending on the particular flutter solution algorithm being used. But at its root, it's essentially a complex eigenvalue equation, and the general outputs are outputs used to make VF and VG plots. So essentially you can get outputs that show how the structural frequencies change as a function of velocity. So as you increase your velocity and dynamic pressure, how does the natural frequencies of the airframe change under the influence of the aerodynamics? And then the other is the damping versus velocity plot. And these equations are formulated such that if you have positive damping, it implies that you have an unstable route. And so you can see, determine roughly what is the velocity at which your damping goes positive, and that's an indication that you're entering into a unstable flutter situation. The third Nastran aeroelastic solution sequence is solution 146. It's essentially our dynamic aeroelastic solution sequence. It's a frequency domain, frequency response solution. It's solved in complex coordinates. So you have, again, generalized mass, generalized damping, generalized stiffness, and again, generalized aerodynamics, and then modal displacements come out at the end. There is a transient response formulation, but it's not. We do not convert the aerodynamics directly and do any sort of a P-transform or anything like that. In this case, we're just doing a Fourier transform on the equation of motion, and so we can apply time-dependent loads and get to time-dependent responses out using Fourier transform methods. But at its heart, it's a frequency domain solution. And the outputs from this solution would be just standard Nastran dynamic responses, displacements, velocities, accelerations. You can also get the integrated loads from the aerodynamics on any region of the structure, as well as the standard element forces and strains. And there is a random response capability that you can get as well, so you can get output power spectral densities, root mean square values, and zero crossings for inputs to fatigue and things like that. So what is MSC Flightloads? So MSC Flightloads is a graphical interface for the Nastran aeroelastic solution, and it's hosted as an optional module to Patrans. So you'll see when I show you the demonstration that when I fire up Flightloads, you see it's going to look just like what Patran looks, except that it's got one extra little button over here on the right called Flightloads. And when you click on that Flightloads button, it brings up this menu system on the right-hand side. And when you interface with Flightloads, you're essentially working down through these radio buttons to do things like create the aero mesh or import aero meshes and do various results processing and things like that. It can display, of course, just the structure, but it also can display an aerodynamic mesh. I'm showing a doublet lattice mesh for this simple example here today. It does have an ability to import the general Nastran 3D aero mesh. If any of you have looked in the recent release of Nastran, the AE Quad, AE Tria type general 3D surface that some customers are using to interface up through to bring in displacements for CFD, etc. So it can import that as well, although we're just going to focus only on doublet lattice today. So some of the basic features of MSC Flightloads is it enables you to create your aeroelastic model. And so by your aeroelastic model, I mean it can create the aerodynamic mesh using the native Nastran aerodynamic methods. So for example, you can create the aerodynamic mesh for doublet lattice aerodynamics, which is a subsonic code, panel code, zone of 51 or constant pressure method, which is supersonic code. Excuse me. It can also create and display slender body aerodynamics. It can create the control surfaces so that you can have controllers for things like elevator and aileron deflection. And then it does some checking as well. No, demonstrate this, how you can do Nyquist criteria or boxes per wavelength checks and aspect ratio checks on your aero mesh to verify that your mesh is adequate for your situation. So I'm going to go right now into a brief demonstration, and I'm going to first import a doublet lattice mesh into an existing model. I'm going to show some of the mesh validation, and then I'm just going to quickly show you some of the meshing options. Okay, so this is Patran. I'm happy to be running Patran 2008 R2, which is what I have currently installed on my laptop here. And this is just the structural model that I imported originally. And I'm going to, you notice right now the Flightloads icon is grayed out. And that's because when you fire up Flightloads by default, it's really just firing up Patran. But it's fired it up with the option of turning on the Flightloads area. So when I first fired up Patran, my default preference came in saying that the analysis type was structural. So as long as I'm in the structural preference, it's exactly like Patran, which you may be familiar with. If I toggle down here to say Aeroelasticity now the Flightloads icon is now available for me. I can click on it, and now I've got my Flightloads form here. So what I'm going to do, since I already have a Nastran, I happen to have a Nastran input file for this entire aircraft with the doublet lattice mesh already created. So I'm first going to just show you how I can import that. So I'm going to come over to import, and I'm going to import this particular model. It's doing the import right now. And it's actually running a little Nastran job in the background that's processing just the Aeroelastic elements of the model. And it's Patran's now reading that data from the Nastran database that's being run in the background. And you can see some of it, the graphics being updated. So let me now go here and let me just post. You'll notice here I now have in my groups posted, the default group is just my structure. That's what I've got right here. But if I come back, I also have an aerodynamic Aeroelastic group now that's been created upon import, and I can post that. And this is just my doublet lattice aero mesh here. It's broken up into various panels and sections. The various panels and sections here are all individually selectable, so I can go and select any individual section of doublet lattice panels as well. So, okay, let me go back and post the whole aerodynamic mesh. Now, this is my mesh. Maybe I inherited this, and the reason I showed this import is because there's a large number of users of Nastran Aeroelastic solutions around the world, and there's still quite a few that haven't been exposed or haven't used a Flightload. So most Aeroelastic users, oftentimes they inherit a model, and they're going to use it for some downstream analysis. So one of the first things you want to do is verify that the mesh that you receive is going to be adequate for your studies. So if I come in here to the aero modeling form, normally in aero modeling, this is where I can go in and I can do things such as create, modify, and delete these various lifting surfaces. And I'll show you that in a minute. But I also can come down here to show, and I can show the lifting surface aspect ratio. So if I simply go and select apply here, you can see the aspect ratio is set to a maximum of 3. This is the default recommendation for doublet lattice with our standard doublet lattice method, that you don't exceed an aspect ratio of 3. And so it's highlighting, making a fringe plot of the various aspect ratios. And if I hit plot failed elements only, it will only highlight the elements that exceed that aspect ratio of 3. So if I inherited this model, what I might want to do is come through. You can see I've got some elements in various places with a little bit larger aspect ratio than desired. So I would tend to want to remesh this and remesh it in the spanwise direction so that I would reduce these aspect ratios. So that's the aspect ratio check. And then the other one that's for unsteady aerodynamics in particular is important is this Nyquist criteria, also called the boxes per wavelength criteria. It's basically how many boxes in the chordwise direction to capture the oscillatory aerodynamics effectively. And there's a couple of different ways to input the data, but generally you can input it in either physical dimensional units or in non-dimensionalized units. So I'll stick with dimensional. And in this case, I'm going to say my minimum velocity of interest, say for some flutter solution later on, is about 4,000 inches per second. And my maximum cyclic frequency, let's say originally, I'm not really sure, and I'm going to say, well, maybe it's up to 50 hertz. So if I come in here and say apply here, the recommendation from MSC is that you have at least 15 boxes per wavelength when you're doing unsteady aerodynamics, and that's somewhat subjective. But you can see here in the plot that I have, I do have in some areas I have quite a few boxes per wavelength, up to maybe 185 in some regions of the mesh. And down here I'm somewhere between 0 and 21. So I'm not too far off, but I still may have some boxes less than 15. So let me go and say plot failed boxes only. And you can see I do have a few boxes in the middle here that are less than 15 boxes per wavelength. So if in fact for say my flutter analysis I determined that I had significant modes up to 50 hertz that I needed to capture or that may play a role in my flutter solution, it would behoove me to go and refine my mesh in the chordwise direction and try and reduce this down or increase this to at least 15 boxes per wavelength. Now I happen to know for this particular solution that the flutter events in the sample problem at least are well below 50 hertz, and they're more closer to less than even 20 hertz. So I'm going to go and reset the maximum velocity or frequency to 30 hertz and reapply. And in that case, I see if my maximum cyclic frequency is 30 hertz, now my mesh comes out. I have no boxes plotted. And so this mesh ought to be okay for unsteady aeroelastic analysis if I've got a maximum frequency of 30 hertz and my minimum velocity is 4,000 inches per second. Now, in terms of creating these various doublet lattice panels, let me go here and just plot, erase the mesh, and I've got this underlined geometry that you see here. This geometry was created when I imported the aero mesh. It automatically created a geometrical surface for each aerodynamic panel that it found in the Nastran run. And it creates this so that if you do decide you need to refine your mesh, it's very easy to refine. You've already got a piece of geometry that you can mesh. And the meshing, quite frankly, is pretty simple when it comes to creating a doublet lattice mesh because these are all just parallelograms, flat surfaces. So the meshing is not complicated. So I'm going to, I can create a doublet lattice lifting surface using, there's several methods. If I pick existing surface, it means I've got an existing geometrical surface. So I can give it the surface a name. I'll just say right inboard wing. I can select, say, this surface right here, and I can come in here, and I've got various meshing options for either uniform meshing or biased meshing, or some sort of tabular input of mesh. So for my spanwise mesh, I'm just going to say uniform, and I'll go with, say, 15 boxes. And for my chordwise mesh, I can do, let's say, a two-way bias, so that I can get the mesh, higher mesh density at the leading and trailing edges where oftentimes there's increased pressure gradients. So I can go, let's say, with, say, 16 boxes in the chordwise direction, and I want the boxes, say, in the middle to be roughly 3 times larger than those at the leading edge. And so I can simply say, apply now. What did I do with my form here, and there is a little doublet lattice mesh that was just created for this panel. Now, of course, I still have the other mesh that was there on that panel as well, so I'm not going to move forward with this. I'm going to go ahead and just delete this right now, so I don't mix myself up later on. But that's the basics of the demonstration for this. And you would go through and you could create the mesh for the different panels, and after you've got the mesh, you would eventually couple them to your structure, so we'll come back to that in a minute. Let me get back and post my SIM. Okay, the next thing I wanted to talk about is the aeroelastic side. So we can create the splines to couple the aeroelastic or the aerodynamic mesh to the structure. Nastran has a fairly rich library of aerostructure coupling methods. All of them use splining techniques, which essentially use finite element type plates and beam theory as mechanisms to distribute the loads and displacements back and forth between the meshes. Some of the splining methods are suitable for just two-dimensional aerodynamics like doublet lattice, and some of them, like the spline 6 and 7, have been used for 3 to 6 DOF splining between Nastran and things like CFD type meshes. Also on the aeroelastic side in Flightloads, you can create the static aeroelasticity setup, so you can define the controllers and the trim model setup. You can also do a little bit of the flutter setup and export the Nastran model to do the aeroelastic analysis. So let me give you just a brief demonstration on the splining side, and if I have a little time, I'll also show you a little bit on the monitor point side. So this is our aero mesh, and if I come back to post my structure as well, I've now got the structure and the aero mesh posted. Now, since I inherited this model, another thing that's often of interest is I want to know, well, gee, someone gave me this model. There's a bunch of splines in the model. In fact, I can come in here, and if I go to aerostructure coupling, I can actually say show. When I imported this, let me look at all the different splines in this model. So there's various splines, and as I highlight them, you might be able to see these little regions in blue getting highlighted that are defining the structure and the aero mesh regions. If again I just come back to post, let me post the aero mesh for just a minute here only. And again, you can see as I highlight the different splines, you can see which spline corresponds to the mapping between a particular aerodynamic panel. Put the structure back on here. So this is handy just to see the various interpolation regions. So each spline essentially is an interpolation region that will interpolate loads. It will map loads from the aerodynamics onto the structure, and it will also map structural displacements onto the aerodynamics. So one of the first things you generally want to do as you're creating splines is to validate that those splines are capable of mapping the displacements from the structure back to the aero mesh. So Flightloads has a convenient mechanism to do that. I first have to bring some displacements in on this model, so I'm going to attach a results file that contains normal mode shapes. So I happen to have a database, an XDB file that's got the mode shapes of this from the normal mode solution 103 calculation. And if I just look in the results here, you can see I've got various modes. If I look at mode 7, for example, you can see I've got the this is the first wing bending mode, and we've got various other modes. So these are just the mode shapes of this aircraft. Okay, so once I've got these mode shapes, I can come back into the aeroelasticity, aerostructure coupling, and I haven't created any splines yet, but I have splines in this database already from the import, so I'm going to skip creation for just a minute, and I'm going to come down right to verify. And I can verify my splines by doing a displacement animation. So I'm going to just come through and select all the splines in my model for this validation. And now down here, I'm going to use eigenvectors as the verification result. And I'm going to pick mode 8. Now, generally, if I'm doing a flutter solution, I'm going to want to look at the modes that my engineering experience tells me are significant and oftentimes play a role in flutter. And I want to verify that the displacements of my structure for those modes will map back to the aero mesh properly. So that's typically the bending and torsional modes and control system modes and things like that. So if we look at mode 8 here, I'm going to hit apply. And what's happening is Flightloads is actually launching a Nastran job, and it's sending, that's the wrong, actually wanted mode 7. Let me come back. I'll explain this in a second. Mode 7 is the first wing bending mode. So what this is doing, what just happened there is Flightloads exported a Nastran file of the spline definitions and of the structure, and it had Nastran create the spline matrices. Once it had the spline matrices, then Nastran threw the displacements from the XDB file onto that Nastran database, and Nastran did a matrix multiply to map those displacements onto the aero mesh. So we see the aero mesh moving in red and the structure moving in white for the first wing bending mode. And so if we step through this, you can see the aero mesh is in fact bending with the structure. Out here at the tail, you might see it looks like the aero mesh isn't moving. Well, this is because doublet lattice, this is, some of you may or may not be familiar with this. Doublet lattice is a simplified, it's not a 6-dimensional aerodynamic theory. It only has 2 degrees of freedom. It only has a normal motion and a pitching motion. So it's got 1 rotational degree of freedom and 1 vertical translational degree of freedom. So the tail out here is only going to have motion in the lateral direction and in the twisting direction of the tail. Okay, so if we go and look at some of the other modes, here's mode 10. So again, this one we get the rotation of the tail and unsymmetric wing mode. And again, what you see here, if we advance through this, it looks like, you know, perhaps maybe we don't have good connectivity between the wing and the structure here. But really what's happening here is there's fore-aft motion of the wing. So again, doublet lattice does not have any fore-aft motion. It only has vertical motion and twisting motion. So the fore-aft motion of the structure is just not connected to the aero mesh at all because there's no place in the aerodynamic degree of freedom to capture that. So again, if we look at this head-on, we can see that the aero mesh is in fact bending in concert with the structure. So again, this looks reasonable. And we can see that the empennage is rotating with the structure as well. So there's a little bit of an art to interpreting this output, but generally speaking, you know, this looks reasonable. Okay, so that's the interactive spline verification, and where this is used is that if there is an art to creating splines and figuring out, you know, how many nodes you want to connect to and how much you want to connect to grids that are outside your various aero panels and how much smearing you kind of want to do between panels. And so what's nice about this is as you go and create a particular spline, once you create it, let's say I'm going to create a spline, I'll just call it again wing spline. I'm not actually going to do this here, but generally when you create a spline, all you're doing is you're selecting sets of structural nodes. So if I come in here and post just my structure, I can come in here and I can arbitrarily just grab a bunch of nodes, and that's not always the wisest thing to do when you're creating splines. So typically you would want to go and kind of create groups of what I call nodes that are good candidates for splining. So they're nodes that have that can carry load without having large displacements and things like that that will cause perturbations in the aerodynamics due to a load. But generally speaking, you're going to pick node, or if you have groups created, you're going to go and select the group, and you'll create a spline with that group of nodes. And then on the aero mesh, you're going to go and apply that group of nodes to one or more aerodynamic panels. And so essentially that's what you're doing with splining. And so if you create a spline with a group of nodes and a group of panels, you can then come in here to the input data and say whether that spline can be used for mapping forces or displacements or both, whether you're going to put any flexibility in that. These are just little knobs on some of the splines. And also, I didn't show it, but you know, there's various types of splines that can be created in this form. Now, if I went ahead and said apply, I'm not going to do it, but if I applied it and created a new spline, I could immediately go right into verify and have it do a verification of that specific spline and see how that spline moves with the various modes to see if it's satisfying my criteria. The last thing I want to show related to the Aeroelastic modeling is this structural monitor points. Now, some of you may or may not be familiar with what monitor points are, but monitor points is just a general term for what I call load sensors. and they're used, the loads community, people that are doing flight loads, dynamic and static flight loads with Nastran make heavy use of them. Essentially, they're sort of things you can instrument your Nastran finite element model with, and they're nothing more than collections of grids. And what the program will do is integrate the aerodynamic loads, and in the static case, also the option of internal loads on those collections of grids, so you can get integrated load points to create things like shear moment torque plots and such. So this model happens to have a lot of monitor points on it already, so you can see the ones that are named. So for example, if I click on, I have it set to show, so if I click on the right wing structure outboard spline, I don't know if you can see it too well, but let me get in this mode here. You can now see these highlights. These set of grids out here that are highlighted are one integration region. And so in my Nastran solution, if I run solution 144, you're going to get these various monitor point outputs for each particular component. So I don't have it, but somewhere down here near the bottom would be the component for that right outboard wing section. And it will give you the integrated loads due to the rigid aerodynamics. It will give you the integrated loads due to the combination of the rigid aerodynamics and the elastic displacement. So this second column is the total aerodynamic force due to the deflection. And then also the inertial loads. What's the integrated loads due to the acceleration taking place? If you have other additional applied loads on your structure, they can be summed up as well. So this data, if you select to create monitor points for different regions, usually people will create monitor points for different cuts of the wing. So you might have this wing broken into 10 or 20 cuts. And then you get the integrated load at each section cut, and then you use that input to make the shear moment torque plots along the wings and along the fuselages and things like that. And again, in terms of creating monitor points, it's somewhat similar to splines. You would give it a name, give it a label, you specify the location and space about which you want that load to be integrated. You specify the coordinate system that you're using for the reference to locate the monitor points in space. And then you also have an optional coordinate system that defines the output orientation of the loads. And then you simply go in and grab a bunch of nodes and say, here's the set of nodes that I want to use in a particular region. And on the input data, you can specify which coordinates you want to sum the loads up, and by default, you get all 6 degrees of freedom. So it's pretty simple to set up a particular monitor point. Okay, I'm short on time, so I'm going to move forward here. On the post-processing side in Flightloads, we can look at the rigid and elastic pressure distributions on the aero or the structural mesh. We can look at deformations on the aero mesh. And again, we can look at things like animations, and the ones that are always fun to look at are the flutter mode animations. It's always nice to see those complex eigenvalues animating. I'm not going to demonstrate it today, but there is a tool in Flightloads, something called the Loads Browser, where you can create shear moment torque plots as a post-processing step. It doesn't actually use the monitor points created from Nastran, but it uses the actual the loads, the Flightloads computed by the Nastran solution, and it post-processes them on the fly to create VMT plots and such. So I'm going to go through and give you a brief demonstration of the 3 bullet items shown here. So first, let me post just the aero mesh. And on this aero mesh, let me come into Results Browser. In Results Viewer, whoops, I got to go and post the right set of modes. Let me go back and go to Results Browser, and I need to access another XDB file. So I'm attaching the XDB file that has the static flight load solution now. So now I still got all those mode shapes from before, but now I've got 2 additional cases that were brought in. The first case is the results available on the aerodynamic mesh. The second case is the same results, but for display on the structural mesh. We've got them separated for simplicity. So I can come here on the aero mesh, and I can simply come in here and say, let's just look at the displacements. Now, this particular solution was just was a static aeroelastic solution due to a 1G level flight condition of this little aircraft. And so if we look at it, this is the wing deflections displayed. It's highly magnified for visualization purposes, but it looks reasonable. You got the wings bending up under display. You got a little bit of downward pressure, or a little bit of display due to the angle of attack change for level flight on the empennage. Now I can also make plots. I can make let me do a fringe plot here. Turn off the display. I can look at the rigid or the elastic increment pressure. So if I look at the rigid element, the aeroelastic pressure, the rigid component, this is the rigid pressures due to the 1G level flight. So the rigid pressures due to rigid aerodynamics. I can also come down here and look at the elastic increment. So this is the pressure distribution just due to the incremental structural deflection. And this model is fairly stiff, so there's not actually that interesting. You do get a little bit more of interest back here in the tail. Okay, so that's the pressure display, but sometimes it's more meaningful to look at the some of the loads displayed. So for that, it's easier to do what I call a marker plot and to look at a vector plot. And let me first refresh my graphics here. And if I come in here and what am I looking at here? Want to get, why is this doing case IDs? Okay, so this vector plot is the aerodynamic forces on the various aerodynamic nodes. I can clean this up quite a bit by turning off the vector label. And you can see from the color coding what's the magnitude of the various plots. And I can go in here and change it so that the various arrows are scaled based upon their values. And now we can see where you get greater and lesser forces. Now, of course, this is a little bit misleading when you're looking at forces because the aerodynamic elements that have more area will tend to pick up a larger force because the force is the pressure times the area. But nonetheless, you can see where things are, and you can see that you're, as expected, you pick up the majority of the force near the leading edges, etc. Now, we can also go and on the structure. We can post this on the structural model. And I can go and plot the rigid forces on the structure. Now what we're seeing here is the same arrows, and this actually is kind of an interesting plot. I was looking at this yesterday when I inherited this model. You're going to see a load. Let me first turn off the, make this so that it's just a constant arrow length. Every place there's an arrow here is a grid point that's connected to the aerodynamics through a spline. So every spline grid has some load. Now some of them may be very small, but nonetheless you get some. Now if I come over here and set it to scale the displacements, you can see it's dominated by, I get a big spike in load here. This is indicative I probably have a splining issue where maybe I'm doing something in one of my splines and then for whatever reason I'm getting a disproportionate amount of load dumped to this region of my model. So it's clear to me that my splines in this model are not symmetric. I don't have the same symmetric grids chosen on the left and right side. And I could go through and do some explorations to see the grids in that spline and figure out what's going on there. But nonetheless, that's why this is useful for these types of plots. You can help see these sorts of things going on. Now, I can also look at the total balanced loads. So if I look at the applied loads, this will be the aerodynamic loads and the inertial loads. total, so it's balanced, and it doesn't look that interesting because there's a big lumped mass here that dominates, and on the rest of the airframe, you can't really see it if I zoom in. There are little teeny loads on the airframe. I still can't, I almost can't see them there. But they're out there. If I come back here to turning off the scaled, now we can see the loads. But these are the balanced loads, and because we've got very little bits of mass, the actual mass on the structural grid is very small compared to this big lumped mass here in the center. But if this is the balanced load set, and we could do things in Flightloads like export that. I could pick the export either fragments or export load data. So I could export either the rigid loads, the elastic loads, or the total balanced applied loads and dump them out to a file, and I would get a Nastran file of force cards that I could use and pass downstream to one of my engineers who needed the loads for a downstream portion of the Nastran model. So anyhow, that's pretty much it in a nutshell. So, in summary, the Flightloads product to give you a tool to create, import Nastran Aeroelastic models, as well as export Nastran Aeroelastic models. I didn't show the export step, but you can export either the entire Nastran model with the Aeroelastic model in it, or oftentimes is the case, the guy that's building the Aeroelastic model is maybe separate than the guy that's building the structural model. So there's a way to export just the, what I call the bulk data fragments of the Aeroelastic model. So you can export just the Sierra panels, or just individual splines, or just monitor points, so that the downstream engineer that controls the finite element model can just include those particular pieces of the model directly into his model. You can also create splines. You can do the visualization of the grid points and the boxes in the splines, and you can do the verification of the splines by doing displacement animation. We can also look at the Aeroelastic results on either the structure mesh or the Aeroelastic model. So that's it for me. Jeff, I'm open for questions. I haven't looked to see if there's been any questions during the presentation, but I'm able to answer any questions at this point.
Okay, great. As a matter of fact, one question just came in, and the question is the aircraft model and deck used in this demo available? So,
yes, this model is available. As many of you know, in the aerospace industry, almost all real aero models are always company proprietary. So, so this particular model is available. It's in our TPL library, in the Nastran test problem library, but I can also send it out as well. Or maybe, Jeff, I don't know if we can zip it up and package it with this delivery in some form.
But as a matter of fact, Jack, yes, it's an interesting segue, because what I'm going to do is, if everybody looks in your chat window right now, the answer to Todd's question there is a link. And if you copy that link, that is a link to our SimCompanion article on this particular webinar. Today it leads you to the registration page. But in a couple of days, what we're going to do is we've been recording this particular the session here, and we will put a recording of this session in that article, as well as any relevant data. And so if you send me all the data, Jack, I'll go ahead and add that as an attachment to that article.
Okay, yeah, I can do that. And the name of the model, for those of you that might have your Nastran installation today, in the TPL subdirectory of the Nastran installation, it's just called Free DLM, F-R-E-E-D-L-M. It's free. It's this aircraft is a not necessarily. It looks realistic, but there's a lot of the actual properties. We didn't have the real aircraft model. But there was an engineer at a company that we worked with who had the kit version of this aircraft in his garage, and so he helped us come up with some approximate properties for this, and it's modeled off of a Lancer Freedom 4 aircraft. So it was entirely built for non-proprietary use amongst customers as a test bed for aeroelastic analysis for a lot of our demonstrations.
Okay, Jack, there's a question that came into the chat panel I'm just going to read out. It's from David. the question is, did you show the flutter modes?
Oh, I'm sorry, I did not. Let me go back and do that, if we don't mind that. I had just overlooked that. So let me go and
I see that question.
go back to results browser. For simplicity, let me first just detach the XDB files I already have, and I'm going to reattach one for Flutter. Okay, I have a Flutter solution of this, Freedom 4 Free Flutter. Okay, I can simply come down in here now into the results viewer, and actually let me first in my, this is the Nastran Flutter solution. 1 minute here, I'm moving something out of the way on my desktop here. This is the F06 file from a Nastran Solution 145 run, and there's quite a bit of input in it. But in the end, in these Flutter solutions, you get a Flutter solution for what they call each solution point. And it's not exact, but generally each point roughly corresponds to a particular mode in the system. And so in this case, this wasn't a complete Flutter analysis, but I did a solution at 5 or 6 different velocities here, ranging from 4,000 inches per second true airspeed up to 8,000 inches per second true airspeed. And we can see that the frequency of the 8th mode roughly varied from about 15.4 hertz at 4,000 inches per second, and you can see it moving around a bit as we add aerodynamics. And more importantly, what we see is the damping. It was stable. We had what's called negative damping at 4,000 and 5,000 inches per second, and then the solution at 6,000 inches per second, we had positive damping. So I can't tell you at this point what the flutter velocity is, but I can tell you that we enter a flutter event somewhere between 5,000 and 6,000 inches per second. So as an engineer, what I would typically do here now is repeat this analysis, and I would refine my velocity distribution to do solutions now between 5,000 and 6,000 inches per second at perhaps maybe 20 inch per second or 100 inch per second increments. So if I look here, though, I can see that this particular, I am fluttering, and this particular complex route has a velocity of 18.03 hertz. So if I come back in here into Patran now, and I look at my, what am I looking at? Results viewer. I want to create a quick plot. I've got actually the normal modes as well as the complex modes in this, and so the second block of modes is the complex routes from the Flutter solution. So there's a whole bunch, all of these are all various complex routes. Some of them represent stable solutions, some represent unstable solutions. That particular route at the 18 hertz was this mode 22. And so if I simply come in here and say I want to do an eigenvector animation, when we animate a complex result, whether it's a complex frequency response result or a complex eigenvector, it defaults by animating through phase angles. So it's going to compute the displacements at various phase angles. So I'm going to go and tell it to do 37 different frames, and that will give me a result at 0 degrees phase angle, 10 degrees, 20 degrees, 30 degrees, all the way up to 360. So it's about every 10 degrees of phase angle. And so now I'm building that animation right now. And we can see it right here. So let me go and just clean up the display a little bit here. Let me turn off my deform mesh. And let me also show this in a shaded view. And let's come back and repeat this. And it will show up even a little nicer if I come into this view. So we can see this is the particular route, unstable route animation for that particular mode. So it looks like it's a torsion bending and perhaps some aileron play going on in there. And just for fun, I mean, I can click on any of these routes. I don't know what they particularly look like, but well, that's a strange one there. I don't know what that is in this model. I want to test that this model is a perfect. Here's another.
That could be a spline problem.
Yeah, it could be a spline problem. It could be there may be a grounding in the tail. anyhow, so this is the basic case. So if you have a flutter solution, the rule is you're going to go in here and you want to look for the frequency associated with the root of interest, and then come down through Patran and identify that frequency and do the animation. Now, this particular model, it's used for testing a lot of different pieces of the Nastran Aeroelastic solutions, but again, it's not 100% real, so you can use it as a guide, but I wouldn't say that, if you see, strange results on this, I wouldn't say that, it's certainly not a perfect model. We don't have access to the real aircraft, but nonetheless, it demonstrates the setup. The splining is reasonable in it, and it's got some monitor points demonstrating that as well, so it's got a lot of good content in it. Okay.
Okay, next question. Can you display the real and complex parts separately?
I can display the real modes. I don't know if I mean real and imaginary part. Yeah, actually, I think that's maybe what was meant here. So let me get out of animate, and if I click again on, say, this particular route, and I come back here to display. Actually, I think I need to do this under deformation plot.
Yeah, it's under plot options, I think.
Actually, let me get this out here. I come back to that mode 18.
Next one over there.
I can go and display, for just a static deformation, it's hard to show a complex route as a static plot. So we could deform, I can show either the magnitude, so again you can see there's definitely some grounding things in here, some RBEs or something not moving in here. But I can show that, the magnitude, I can show just the real value, so this is the real, or I can show a deformation of the imaginary. The imaginary, what does it mean when you deform by an imaginary phase? But anyhow, it lets you display. I can put in anything I want, or I can come in and say at an angle, I can say show me what it is at 45 degrees. So 45 degrees phase angle, this is the deformation. So again though, with complex values, so you can look and display, make a deformation. It doesn't always make sense to make a deformation, but it will deform the grids by the value of the magnitude of the complex number. It will deform the grids by the real component. It will deform the grids by the imaginary component, by the phase component, or by the deformation associated with a particular phase angle. Of course, you can also do marker plots. So maybe for the imaginary component, you would rather see, a marker plot or a fringe plot or something of the imaginary values. So all of that's available.
Okay.
Okay.
Go ahead. At this time, I don't see any other questions here, so I'm going to go ahead and take control back, Jack, if you don't mind.
Okay.
All right. And let me go to my last slide here. If anybody would like to go further and ask any more questions, you can always discuss this with the experts in our community forums at forums.mscsoftware.com, or you can browse our knowledge base at simcompanion.mscsoftware.com. And the link I sent everyone, which I'm going to paste again in the chat window for all participants, is the actual link to this particular webinar. Now, if you log into SimCompanion and you take a look at this webinar, there's a button to subscribe to it. And if you subscribe to it, you will get an email notification once we update it with the webinar materials. And finally, if you need technical support, you can obtain technical support from MSC Software by going to support.mscsoftware.com/service request. So we thank you once again for joining our SimAcademy webinar series, and we hope to see you next time. Thank you.